Hello, today I'm going to be talking about UL-VIO, ultra lightweight visual inertial odometry with noise robust test time adaptation. My name is Jinho Park from Columbia University, advised by Professor Mingoo Seok, and this is joint work with Professor Chun of Seoul National University. So I'm going to go over the table of contents, briefly tell you about motivation, and go over learning-based VIO method, and talk about our results on model compression and noise robust test time adaptation, and end this presentation with conclusion. So the motivation for lightness and robustness is that we need a lightweight neural network to be hosted entirely by on-chip memory, and which is nowadays only of a few megabytes in modern processors. And we want the model to be robust to environmental factors and noises, and that shall reduce distribution shifts, incurring low accuracy. And so I'm going to go over the learning-based VIO pipeline. So given a sequence of visual and inertial inputs, and the visual encoder deduces visual feature from pairwise images, VT and VT plus 1, and inertial encoders does so with the inertial input, obviously, and the decoder will use these features to predict post-transformation. And we perform model compression by performing the following. So we add average pooling after the last convolution layer, and along with channel scaling, this gives us 117 times reduction in visual encoder, and reduce the channel size of inertial encoder, and we obtain about 8 times reduction. And finally, we replace the LSTM with a fully connected layer for the fused decoder, and this gives us 160 times downsizing in the F. And we achieve 36 times model size reduction with a minute increase in the absolute post-estimation error. And previous studies neglected the model size consideration, which is a major bottleneck in edge deployment. And for example, latest Apple A16 or Qualcomm Snapdragon CPUs possess only a few megabytes of on-chip memory. And this is the odometry results of Kitty, and ours with model compression has a slight deviation on sequence 7 and have a better ego motion in sequence 10 than modality selection and NAS-VIO. For UROC dataset, ours perform comparably to modality selection and hard fusion with over 50 times reduction. And this is a proposed TTA with multimodal consistency. Having the original VIO network, the visual inputs now experience noise shifts from the environment, and we dedicate a separate inertial decoder that only uses the inertial feature. We adapt the network based on the inertial only feature at test time. And I'm going to talk about the dictionary-based adaptation. This is the visualization of the visual encoder. So 4-path generates the visual feature, and which will be used by the decoder, the deeper layers, as I've said before. And the first layer, convolutional output, is used to deduce a domain distinctive feature as a DDF shortened, and the domain is found by using L2 distance with the proxies or references. And the Batchman parameters corresponding to the domain are solely updated according to the algorithm. So this is a result when we compare it with the fine-tuned baselines. We demonstrate the effectiveness of our TTA by comparing it to our fine-tuned ones with adversarial noises. And except for one case, for example, the multiplicative noise, our TTA method has the best or second best accuracy. And this is online TTA and corresponding trajectory results. Translation RMSE quickly increases when there is a visual corruption, and TTA mitigates the increase in the error to some extent. And noise injected causes the trajectory to be underestimated, but this is alleviated with TTA. And this is the work on continual TTA. And we inject different types of noises, blur, rain, snow, contrast for a kitty. And we apply other visual corruptions relatable to indoor setting for UROC. And TTA effectively reduces the translation RMSE. So in conclusion, we achieve a network with less than 1 million parameters through model compression. That is 36 times less than state of the art. And we effectively reduce the post-estimation error with multimodal consistency-based TTA.